All right, welcome back. Here we're looking again at the work energy theorem. There's just a couple minor points about this idea of kinetic energy, which is a new idea for us, that I want to make, and then we'll look at an example. Kinetic energy, first of all. Sometimes you'll see a K. That's how our textbook works it. Sometimes you'll see kinetic energy, KE. That's fine. The simplest way of thinking of this is the energy of motion. And the reason is, if you think about the relationship between kinetic energy and mass and velocity, if there is no motion, if velocity is zero, well, you have no kinetic energy. So that's relatively easy to understand, no big deal. Now, another interesting note about kinetic energy here, you know that velocity is a vector. The direction of your velocity matters. You can have in the horizontal direction a positive or negative velocity. You can have in the vertical direction a positive or negative velocity. In fact, velocity can be in any direction. And if it's at some more interesting direction, then you can break it up into vertical and horizontal components, sign on each of those components. Okay, fine. But what happens to direction of something when you square it, or when you cube it, or when you have the square root, or anything else? It sort of becomes meaningless. The direction itself does. What that tells us is that kinetic energy does not have a direction to it. Like work, it's a scalar quantity. Scalar simply meaning that it has size but no direction. So it's like work in that regard. It is unlike work, though, in one other kind of important characteristic. Kinetic energy was always going to be a positive value, or zero, I should say. I should include that. You could have zero kinetic energy. But a kinetic energy will never be negative. You might have a velocity in the negative direction, but when you square that value, you end up with a positive. Mass cannot be negative. You either have a positive value or you have no mass, which is just kind of lame. And so the idea of having kinetic energy always be positive or zero is kind of important. And it's different from work in this regard. Work could be positive or negative, even though work is a scalar. Direction of work doesn't really matter. The reason work needs to be either positive or negative, the reason why that matters is because you do need to add work together, and some work can cancel other work if the signs are different. Okay, so we have some interesting characteristics here to this idea of kinetic energy. It's a scalar, there's no direction to energy, and energy of any kind, to be perfectly honest. Kinetic is the first kind we're looking at, energy of motion. But there's no direction to it. There is direction to the motion, there's direction to the velocity, not to the kinetic energy. And the kinetic energy will either be zero or positive, never negative. All right, cool. So with those in mind, let's look at an interesting example. In fact, I'm just going to start with a new sheet of paper here. This example is going to help us practice using the work energy theorem, the connection between work done on an object and the change in its kinetic energy. And when you're changing kinetic energy, you're going to be changing the velocity. Okay, let's look at an object. Could be a car. So this example going on here. And my artistic skills are absolutely horrendous, so bear with me. Car. All right. And we're going to do work on the car. And now the car is here, but in doing work on it, let's call it work one, we've changed its velocity. We've applied a net force to it, creating an acceleration, and therefore changing its velocity. So initially, the velocity was zero, and now we have a velocity v. Cool. All right. And from velocity v, we're going to do this again. We're going to say, well, I'm going to do some more work on it. And never mind that it looks like it's sloping down. I apologize. It just meant to be a horizontal surface. We're now going to do some more work on it, work 2. And work 2 will give it a velocity, a new velocity now, of 2v. So we will have doubled the velocity from this moment right here. And so what we need to look at is, we're going to make a comparison. In going from 0 to v, how much work was required, and then going from v to 2v, how much work was required. Okay, so first things first, we're going to calculate v1. I'm sorry, we're going to calculate work 1. The work needed to go from rest to that initial velocity, or that velocity v. And so, with our work energy theorem, we know that this is going to be equal to the change in kinetic energy. And the change in kinetic energy is basically our final velocity, take away, final kinetic energy, take away our initial kinetic energy. I'll put V0 there, just so that we can sort of differentiate the two V's, and that'll be squared. I should have 0 here, though. That is my initial velocity that I'm dealing with. And so look what's going on. The initial velocity is 0, so I'm taking nothing away. So the work 1, this first amount of work we did, will have a value equal to 1/2 mv squared. Okay, fair enough. So now, how much work is needed to go from rest, this initial velocity, to this final velocity? Let's work that out. So what are we going to get? We're going to say, how that work total, maybe? Work total, okay. So this work total, well, I know I'm going to have a final velocity of 1/2 m, and this is 2v squared. I'm going to take away my initial amount of kinetic energy, which is taking place when I have my initial velocity. Initial velocity is 0. This whole term goes away. And so the total work is 1/2 m. Now what's interesting here is I have to square that too. Okay, so this is really going to become, if I can sort of factor out that 2 squared, I have a 4 here. Total work is 4 times this quantity. So look what this means. I see the same quantity here, and the total work was 4 times that amount. Total work, sorry about squeezing the 4 in right there. Total work is 4 times this amount here, which is the first amount of work I did. 4 times work 1. So this is very interesting. To get the velocity to be twice as fast, I didn't have to do twice the amount of work. Instead of achieving a final velocity of v, I achieve a final velocity of 2v, twice as fast. In order to do that, I had to do 4 times the amount of work. Well, that's just like what we saw in the previous video, where we said, okay, this business here. In the previous video, we looked at the initial idea of kinetic energy, and we said, well, if velocity doubles, you need 4 times the kinetic energy, or I'm sorry, you achieve 4 times the kinetic energy. Except that we know that kinetic energy, or I should say change in kinetic energy, is equal to the work done. There's this idea that work and energy are the same, and it turns out they're measured the same as well. They have the same units. The units are joules, right? So if I'm going to have, instead of from 0 to v, I'm going to go from 0 to 2v, twice as fast. What I need to do is not twice the amount of work, but 4 times the amount of work. I need to achieve a change in kinetic energy 4 times as large to get the velocity to double. That's kind of an important deal. Keep this in mind. This is a really good example to understand really well. So what does this mean, though? What is work part 2? Okay, this is kind of a simple thing to look at. We know the total work can be equal to the sum of all the individual works that are done, and the sum is just going to be, well, work 1 plus work 2. There's our total. So our unknown, the question initially was here, what is the value of work 2? How much work is required to go from v to 2v? And it turns out it's the total amount of work minus that first bit, that work number 1. And that makes sense. All right. Well, just an interesting thing. We know that the total work is 4 times the work for number 1. So the total is 4 times work 1, and we're taking away work 1. So we're comparing the work done to go from v to 2v, this amount of work, to the amount of work needed to go from 0 to v. We're comparing those two values right here. That's what we're doing. And it turns out that work 2 is equal to 3 times the value of work 1. Not exactly intuitive, but it's worth understanding how we got here. All right. So this is a pretty good example of how work changes energy and how it's related to velocity, or changes in velocity. And you may want to work through this, reread some of these examples in this section of the chapter very carefully, and let me know if you've got any questions, and we'll keep plugging along. Thank you for watching.